Okay, so we're finally at the last chapter 5 topic, and that deals with standard enthalpies of formation. Um, Really, what's happening in the background is Hess's law and taking advantage of the fact that we do have a state function in enthalpy. Um, you don't really need to understand that that is occurring, but I'd like you to be aware of it. Okay, so you don't need to understand how it fits into a Hess's law because we're going to see that there's actually an equation that we use to solve problems that utilize standard enthalpies of formation. Okay, but just kind of realize, like in the grand scheme of things, and you might touch on this more next semester. Um, that's what's happening. We're dealing with state functions, we're dealing with Hess's law, applicable situations, and so we're able to take advantage of these things that we call standard enthalpies of formation. So, what does it mean to be in standard conditions? Okay, and what's formation have to do with anything? Okay, so let's pick this apart. Standard conditions are not STP. Remember, STP just references gases. Okay, so even though the word standard is inside it and it's a little bit confusing, just keep in your mind that standard conditions are something different. Standard conditions have for gases 1 atmosphere. That's kind of like STP. But standard conditions are also applicable to aqueous solutions, okay? And for aqueous solutions, we have 1 molar concentrations, okay? So when I say something's under standard conditions, or whenever we see something indicating that we have standard conditions, always translate that into the gases are 1 atmosphere. The aqueous components are at 1 molar, all right? For liquids and solids, we don't really have a standard condition that's applicable for what we're talking about this semester. The big change then, besides referencing aqueous situations relative to STP, okay, the big change, right, in comparing the two is that you can have any temperature and have standard conditions because it's all about pressures and concentrations, okay? Now, what we'll see is information generally shows up on tables. And in your back of the book, there's an appendix that has delta H information with this funny circle in the top, delta G information, and S information. And these you deal with next semester, so we don't have to worry about them. But this semester is all about delta H. And when you see this funny circle, it's a superscript 0. And what we say is the word not. So we'll see delta H naught. That delta H naught means that we're under standard conditions. Now, the tables in the back of your book and the tables that Chem 101 will give you in problems like this are generally, all right, constructed looking at these conditions but also at 25 degrees Celsius. Okay? So we're going to see a series of delta H's when they have this circle here. That means that we're doing things with standard conditions. All right? So what kind of delta H's are we going to look at? Those for formation reactions. Okay? So we're actually going to see this F placed, usually it's between the delta and the H. Sometimes it's after the H. All right? But whenever you see this subscript F, that stands for delta H naught of formation, or the enthalpy of formation. Formation reactions then are an important thing for us to talk about. Formation reactions always have 1 mole of product, okay? So there's 1 mole of product. That product is a compound, and if you look on the reactant side, all of the reactants are in their elemental form, okay? So if you have elements coming together to make a compound, and you look on that side of the reaction and you see they have 1 mole of product, right? Then what you have is a formation reaction, and I can go to that table I referenced earlier. And for that reaction, I can look up its delta H naught, okay? Delta H naught for formations then, because we have this definition where we need a product that's a compound. Well, if we ever have elements then and we're thinking about their formation, well, they don't really have a formation reaction because you have to have a compound. And so delta formation H naught for elements is 0. Okay? So just as a quick little example, before we get into how we use these, so all this is background information to a type of problem that you'll see. Okay? But just as a quick little example to kind of see what I'm talking about here, okay? We can look up delta formation H naught for water, okay? And state matters here. And when we look it up in the table that I'm referencing in the back of your book, okay, in the appendix, or if you were going to use this in a problem in Chem 101, Either one of those situations would give you information, all right, 286 kilojoules, right, per mole, right, as a delta formation H naught for water, right? So then what does this tell us? This could be a delta H I write around, or sorry, right next to the reaction for water's formation, right? If I can find the correct reaction that fits all of those conditions that we talked about down here in the last bit of our lecture, right? So what do I mean by that? How can I use this to write it next to a reaction, right? And then build a thermochemical reaction with the correct mole-to-mole bridges, right? Remember when we talked about delta H as a combustion and we had to have 1 mole of combusted material? Always remember that when we're dealing with delta H of formations, we have to have 1 mole of product. So if I go and I try to write the formation reaction for liquid water, right? What you're going to do is you're going to say, okay, what elements have to come together to make water? That's the definition of formation. On this side, we have to have things in their elemental form. Well, if I want to bring H into play here, so I can make some H's and H2O, what's the elemental form of H? Well, it's hydrogen. And so we have to write that as H2 gas. Let me give myself more space here. All right. What's the elemental form of O? Because remember, fitting the definition of formation, we have to have only elemental forms over here. Well, the elemental form of O is O2 gas. And you always find the state that's most common in like hydrogen, oxygen, those are gaseous states, nitrogen, etc. Right? But then this isn't balanced, right? So early in the semester, what we would do is say, okay, we need a 2 here and a 2 here, and now it's balanced, okay? So if I look at this reaction, this looks like a formation reaction with one big problem. Remember, for formation reactions, we have to have a 1 there, right? So then what I'm going to do is I'm going to divide each and every coefficient by 2. So I'm going to write this as H2 gas plus 1/2 O2 gas yields H2O liquid. And now I have a 1 here. Now on the left-hand side, I just see things in their elemental form. So now I know that the delta H associated with this reaction is minus 286 kilojoules, right? And then notice, if I was going to build an energy to mole bridge here, it would be minus 286 kilojoules per 1 mole of H2O. And that's exactly what this says up here, right? It says that to form 1 mole of H2O, this is how much energy you expect to see. And that's what we see now down here with our thermochemical reaction, okay? So that's what it means to build a formation reaction. And then when you get information about formation reactions, always remember that whatever that number is, you have to compare it to 1 mole of product. All right. Let's look at just one more example, just writing a formation reaction. Yeah, I'm going to incorporate this into your next example. But let's look at delta formation H naught for sodium hydroxide, right? And if we look that up, what we get is it is minus 470 kilojoules per mole, right? Minus 470 kilojoules per mole. So let's write the formation reaction for sodium hydroxide, okay? What we do to write the formation reaction is we go through each and every one of the elements inside the compound, okay? And we try to decide what their elemental form is, and you put it on this side, okay? So that's the first step. So what's the elemental form of sodium? Well, sodium ends in -ium. It doesn't end in GEN or INE. The elemental form of sodium is just a solid chunk of sodium. Now, the elemental form of oxygen is O2 gas, and the elemental form of hydrogen is H2 gas, okay? So it looks like we have a situation where now we've built elements coming together to make a product. That's step number one in a formation reaction. But to use this value here, we need to make sure there's 1 mole in front of the NaOH. Okay? Well, hold on a second. If I go to balance this, right, I'm going to need a 2 here in front of the NaOH, right, to balance out my O's and my H's, and then I would need a 2 here. So what am I going to do? I'm going to divide through by 2 to make sure that there's just a 1 in front of this. Okay? So what I have for the final formation reaction is Na solid plus 1/2 O2 gas plus 1/2 H2 gas yields NaOH solid. Okay? Is this balanced? 1 Na, 1 Na, 1 O, 1 O, 1 H. Yep. It fits everything about, all right, a formation reaction. It fits all our requirements. So now I can write next to this a delta H of minus 470 kilojoules. And then that builds the correct mole to energy ratio that I see up here. All right. So now what do we do with this information? Now that we understand what delta H of formations mean, and we can write formation reactions, okay? How do we use these in problems? Well, it's kind of like Hess's law, where you have a target reaction or an overall reaction. And what you can do is you can use delta formation H naughts to infer an unknown delta H naught, okay? The only difference between this and Hess's law is that the delta H that we calculate is delta H naught. So there's some target reaction where we don't know it's delta H. Well, that sounds like Hess's law, okay? But now, instead of looking at a series of reactions that we put together and flip and manipulate to get everything in the correct spot and then add together to get an overall delta H naught, instead, we're going to use delta formation H naughts, okay? Now, to ID when we're going to do this process that I'm going to show you, right, in a second, you're going to be given a series of these. So the nice thing about Chem 101 is they don't really have you go look in an appendix or anything like that. When you need these, they make a list of delta formation H naughts. Not a list of reactions, but a list of those bits of information. And when you see this, this is how you calculate delta H naught for your target reaction. You do a sum. And you look at the stoichiometric coefficient associated with each product and the delta formation H naught associated with each product. You multiply those together and sum them up for all your products. You do the exact same sum for your reactants, and I'm just going to change the subscript here. You take the stoichiometric coefficient that you see, the delta formation H naught that you see for each reactant. You do 2 sums. And then to calculate delta H naught, you subtract these 2 sums. Okay? So you make a sum for the products, you make a sum for the reactants, and then you subtract. So what are you summing together one more time? Stoichiometric coefficient times the delta formation H naught that's given. All right? Plus, for the next product, stoichiometric coefficient times the delta formation H naught that's given. And then you do the exact same process for reactants and take the total and subtract them. Okay? So this looks like a confusing process until you see a reaction and analyze it in this fashion until you see an example. So let's do an example that utilizes, all right, this process. Getting, again, an unknown delta H from known, and in this time, tabulated delta H's of formation. So if you look at your slideshow, what you'll see is a lot of information that I went over on slide 9. So this is in chapter 5, so your chapter 5 PowerPoint. And then on slide 10, we introduce, okay, a reaction to analyze. And you're to analyze 2Na solid plus 2 H2O liquid, giving 2 NaOH, right, solid, plus H2 gas. Okay. And we don't know the delta H naught. And so we are asked to calculate it. And then look at what you're given on that slide. This is how a Chem 101 problem will look. You're given the formation enthalpy for this, the formation enthalpy for this, the formation enthalpy for this, and the formation enthalpy for this. So then whenever you're given those lists of formation enthalpies, you use that equation that we wrote down here before, right? Let's interpret that equation in the context of this example. Delta H naught for this example, okay, that equation says I look at my product side, all right? And I have to take the number of moles of each product, all right? So I'm gonna write this as N of NaOH times the delta formation H naught of each product, right? And then what I do is I add them together. So I make a sum doing this for each product. So the number of moles of H2, delta formation H naught of H2. So that first thing that I had in parentheses, that first sum, hopefully you can see how it translates here, okay? So we're going to take the 2 and we're going to put it there. We looked up that delta formation H naught. We're going to take the 1 that's in front of the H2 and we're going to put it there. Now you don't only do this sum for the products. You also do the exact same sum for the reactants, but it's the same sort of form. So I'm going to take N for Na, delta formation H naught for Na, and it's a sum. So I'm going to add to it N for H2O, delta formation H naught for H2O. Right? Now I like to remind myself that this is a sum that I have to put in parentheses because what do I do with these two sums? I subtract them. Okay? So now it's just about fitting the correct information into the correct spot. So below this, right, in your notes now, we can go and we can say, okay, well, if I look at that slideshow, all of these delta formation H naughts, they're given. And in fact, my professor told me, hey, this is the formation enthalpy of something in its elemental form. And this is the formation enthalpy of something in its elemental form. And what do I know about that? Even if I didn't have them in the list, we know that the formation enthalpies for elements are 0. Okay? So now I really only have this bit of information, remembering the negative sign, and this bit of information to put into this equation to get a final answer. Because what's anything times 0? It is 0. And if I add 0 to anything, it doesn't change that anything. Okay? So I'm just going to rewrite this now. Simplify it before I do that substitution. Putting those zeros in there tells me that really what I need is the number of moles of NaOH that I see in my reaction and its formation enthalpy, right? And then to subtract the number of moles of water that I see in the reaction and multiply by its formation enthalpy, right? So let's go ahead and let's do that. I see a 2 here, right, in that reaction. So I'm going to put, right, 2 moles here. Delta formation H naught for NaOH. If you look at that slide, or you remember from a previous example, was minus 470 kilojoules per mole. I'm going to subtract what I see in terms of a stoichiometric coefficient in front of water, which was 2. And then delta formation H naught for water, right, had a negative sign and was minus 286 kilojoules. Ooh, 2 moles here, right? Kilojoules per mole. Let me rewrite that so you can see it. Sorry about that. Minus 2 moles. Okay? So now, this happens a lot. You have to pay attention to sign. Like, the easiest error you can have in a problem like this is a sign error. So as you're doing these problems in Chem 101, if you get the wrong answer, just go back and check your work and be really meticulous about your signs. So when I start to do this math, 2 times minus 470, moles cancels with moles, gives me 940, all right? kilojoules with two significant figures because there's only two significant figures here, right? Minus 2 times minus 286 give me a positive value, and this is going to be positive 572 kilojoules, and this has three significant figures. I add these together. This is good to this spot. This is good to this spot, so my answer is going to be good to the tens place. So I get minus 368 kilojoules, but that's only good to the tens place. And so then my final answer is minus 370 kilojoules. Right, minus 370 kilojoules. And this would be the delta H that you would write next to this reaction to make it a thermochemical reaction. Right, to make it a thermochemical reaction. So even though there's all this information at the beginning of this video about what it means to be standard and what a formation reaction is, okay? This is really the crux of the types of problems you'll see. It's not that you won't be asked about those details, but when you see a reaction and you're asked for an unknown delta H, and you don't have a series of reactions like a Hess's law problem, okay, and what you're given instead are formation enthalpies, then this is the way that you attack those problems, okay? So that's it for chapter 5, and what we do for the last week of the semester is we really change gears away from the mathematical end of things, and we get back to describing what must be happening with the chemicals to make the bonds we've been referencing. So we're through the major math part of the course, okay? But you do have a final coming up in a little bit as well, so you shouldn't forget about all this, but just kind of realize that there is a little bit of a gear change when we get into our next set of videos. As always, please, just as always, contact me if you need any help whatsoever.